Hello everybody. I wanted with this post-lecture video, I wanted to show you some additional details related to the circuits we've seen today, related to the amplifier operation of the BJT. These are mainly we could say, details, maybe even curiosities, but I think they are in a way also important as they complete the picture of the amplifier we've seen today, especially because, for example, we've said that when we do the ASC analysis, we work under the assumption that the capacitances we've introduced are such that for the frequency of the AC signal we will be using, the impedance of these capacitances is effectively negligible compared to the other components around. So the question is, what is exactly the role of these capacitances in determining the frequency response of the amplifier? So that's what mainly I would like to explore here with you. And by doing that, I will also discuss an important variation, let's say, of the amplifiers we've seen today. So today we've seen all the amplifiers that we've seen today are all those that had, for example, at least for the emitter bias configuration and for the voltage divider configuration, we said we will put a capacitor on the RE, on the emitter resistor. Now, I would like to show you that if you were to remove that capacitor completely and analyze the circuit without that capacitor, the existence of that capacitor, actually you get a very interesting amplifier. This is, again, let's treat this as a curiosity again, but I think it's worth that you see this just because it creates for you the opportunity to see, let's say, today we've seen really the basics of the BJT as used as an amplifier. This specific thing I wanted to show you about this, the removal of that capacitor in that position, really lets you make a step into looking into some more advanced, let's say a little bit more advanced applications and uses of these circuits as amplifiers. So enjoy this video and I'll see you next time. Bye. Okay, so first of all, let me, I forgot to mention something about when we introduced the small signal model. Sorry, just very quickly, just a moment. So when we discussed today the small signal model, we defined completely the hybrid model and so on and so forth. I forgot to mention which are the other models very briefly. So we said that the name that the model will take, it all depends on which are the two variables you pick. Depending on the variables you pick, as independent variables, you could end up dealing with the so-called T model or a RE model or impedance model and so on and so forth. So just so you know the names of the other models that exist around, but we will focus on the hybrid model as we said today. So the next thing is, and basically the whole thing I wanted to mention to you with this post-lecture video is about the role of the capacitances that we've seen today. So the first one that I wanted to discuss with you is the role of these emitter capacitance. So we've seen this both in the CE2 emitter bias configuration and also in the CE3 emitter voltage divider. Let us, the result is the same, so because the circuits are very similar anyway. So let us discuss which might be the role of this capacitance. So we've seen, you remember that when CE is there, the idea is that the DC analysis basically means analyzing these circuits, this circuit here, in the case of the CE2 configuration, and the AC analysis means looking at this circuit, where you can see that CE has effectively short-circuited RE, and so there is no, the emitter terminal is effectively shorted to ground. That's the assumption we are making, that CE, the impedance of CE is effectively negligible, and so effectively we are shorting the emitter to ground. And this allowed us to simplify enormously, obviously, the analysis for CE2. Effectively, the analysis of CE2 is the same as CE1 in this AC regime. And so the question is, so we've seen all these things, let's say, so let us now discuss the role of CE. So the idea, what we said, based on what we said today, the idea is that we must choose CE in such a way that the impedance, which is 1 over omega CE, the impedance of CE is much smaller than RE. That's the main the requirement we are making. And in this way, effectively, CE shorts the emitter terminal to ground. Now, to be more accurate, what we should consider is that RE in parallel to CE, this has a certain impedance. The total impedance is given by this formula, is the parallel of these two components. So the total impedance has effectively can be written as in this way. So as we see, when in the DC limit, that means omega goes towards 0, this term becomes negligible as compared to 1, and so the total impedance is effectively RE. And that's what we did even previously when we were looking at the DC analysis. The capacitor becomes irrelevant. On the other hand, when omega is much bigger than omega E, let's call it, which is 1 over CE RE, then the total impedance is effectively the impedance of the capacitor. So if omega is large enough in such a way that effectively even this is small, relatively small, if eventually, you know, a few ohm or even smaller, then we can effectively assume that the emitter is shorted to ground, and so everything we've said today holds, and so on and so forth. So seeing things in this way, you know, by looking at the total impedance of this parallel of these two components, allows us then to see things a bit better now. So if we were to plot the total impedance Z total versus frequency, we would expect a plot like this one. That is effectively the total impedance is very close to RE up until you know, omega E, and then it starts to drop, because then the impedance starts to behave like a capacitor, and the impedance of a capacitor drops as 1 over omega. And so this is showing us clearly that if we want that CE shorts to ground the total impedance of this circuit here, RE parallel to CE, we really need to be at omega, you know, bigger than omega E, of omega, where omega E is this quantity. Okay, so Otherwise, what the AEC analysis we did above just is not true, because we cannot assume that this is effectively can be replaced by a short. Okay, so this realization is a fantastic opportunity to ask ourselves, okay, so what happens if CE is not there? What happens to the AEC analysis of this circuit? Let's assume, for example, the CE2 circuit. Imagine this circuit, the emitter bias configuration, where there was no CE. The DC analysis would be obviously the circuit would be the same as the one that we've seen for this circuit. So the DC, for the DC analysis, we would still have to analyze this circuit. But now, for the AEC analysis, we cannot neglect anymore RE if CE is not there, because it won't be, there will be nothing to short the RE. So let's have a look at that. Okay, let's have a look at this nice curiosity, let's say, but it's very important as we will see in a moment. So let us imagine that C was not present. The AEC circuit now would have RE on the emitter. So this means that the equivalent circuit now would look like this. You see that RE is connected on the emitter. Remember, the emitter terminal is here, toward ground. RB has to go toward ground, and ground now is here. So really the circuit should look like that. The analysis here is a tiny bit more complicated, just because now we have RE here, and so we need to take into consideration IE into our analysis. We need to consider this node, and so on and so forth. I don't want to do this analysis too complicated. There is no reason. As I said, I'm doing this just because, so you know, it's a nice curiosity to know, but it's a very important result behind. So you can just stop if you want to have an in-depth look at the equations that I'm using. You can just stop here. There is nothing really complex. It's just I'm using KCL, KVL. There is this the input mesh, which is the input mesh is effectively now this. The output mesh is this one. So I'm really, applying KCL, KVL to these things, and then just doing a lot of algebra. So the final result, if you do the analysis, is that I will try to highlight the differences also with the corresponding results when CE was in. And so RE was shorted to ground effectively in the AEC analysis. So the input impedance would be now RB in parallel to IE plus RE time HFE plus 1. So when CE was considered, was in the circuit, the input impedance was RB in parallel to HIE. Now we see that RB is in parallel to HIE plus RE HFE plus 1. The interesting thing is that now the emitter resistance appears in the input port amplified in its intensity by a factor effectively HFE. And that's interesting. We had seen this before last week when we were dealing with the DC biasing of the BJT circuit in common emitter. So we're not surprised by this, but I think it's interesting that in this configuration the input impedance now depends also from RE. As I said, amplified by a factor HFE. Then the voltage gain. If you do all the steps, using the equations that that are here. You can see all the KCL equations that are here, the KVL for the output mesh, for the KVL for the input mesh, and so on. So if you use all this, you can realize, as we did today, we can calculate AV infinite when RL is not connected to the circuit, and you end up, this is the correct result, using the fact that effectively HFE is large, so this term will effectively dominate over this, we end up with effectively this result. And this is very interesting. We can see that the AV infinite, when RL is not connected, is now completely defined by parameters that we introduced in the circuit. You see, there is no dependence here from parameters of the BJT, like HFE, HIE, or so on and so forth. So we decide RC and RE. And so this means that, and this is effectively the key point I wanted to make by showing you this specific application where CE has been omitted completely. By removing CE, now I have an opportunity to define the voltage amplification of the circuit completely and only by resistors. External parameters anyway. This means that the voltage amplification of the circuit is extremely stable and independent from the quiescent point. This is really the key. Is independent from the quiescent point. So this is really interesting. Okay. If we then connect RL, as we've seen today, we should expect some perturbation of this result. Again, lot of algebra to get the final result, but the final result in the end is here. And as we've seen today, AV, the total amplification when RL is connected, is AV infinite time RL over RC plus RL, as we see so today. So this result doesn't change, of course. And again, as we said today, if RL is larger than RC, then AV is effectively AV infinite. And the current gain, again, after a lot of algebra, we get to a result that again is very similar in principle to what we've seen today. Only thing is that here we need to add this term again, we need to introduce the effect of the RE resistance. And finally, the output impedance is the same as we've seen today for all the other circuits. So I think really I wanted to show you this application of, in the case of when we did not introduce CE at all in the circuit. So really the key result is this one here, that AV infinite would be dependent only from external parameters that we introduce, RC and RE. So, the last thing I wanted to discuss with you is the effect of the other capacitors that were at play in these circuits we've discussed today. So we had the two more capacitors, C in and C out. So let us discuss which is exactly their role and how they what is their role in defining finally the frequency response of my amplifier. So we've seen which is the behavior of these amplifiers in those regions where effectively the impedance of the C in capacitor and the C out capacitors are negligible. So the question is, what happens if they are not negligible? So, or maybe let us analyze the circuit in a way that we can take them into account. And that's what I do effectively down here. Once we've discussed effectively the three configurations we've seen today, CE1, CE2, and CE3, and we've done the analysis under the assumptions that the capacitances are effectively such that at the frequency we're interested, their impedance is effectively negligible. So at the end of all that story, here we are. Let us discuss now what would happen if we were to actually make a more generalized analysis where we actually try to take into account the effect of these capacitances. How would they affect the frequency response? So to do that, let us redraw. Let us consider for simplicity C1. So the circuit that we saw, C1 with fixed bias. Let us consider the AC model of that circuit, but let us keep in C in and C out, as I did here, as you can see. C in and C out. C out is obviously connected to RL, okay? As we had in the initial circuit. Let's go back. It was, what is the first circuit? There you go. C1 fixed bias, C out was here, and eventually our load would be connected to C out. Okay. So let us go back down there. Here we are. Okay, so now to understand exactly how what we are about to do now relates to what we did today when we were assuming that C in and C out were effectively negligible, I've also drawn here where were the signals that we were calling, for example, V in. So if C in was negligible, V in would be at this point, just before RB. We can go back to the circuit we were looking at today when we were analyzing in AC C1, which was this one here. As you can see, just before RB is what we used to call V in tilde. Okay? While V out is what we used to call just after RC. And so let us put them on that circuit here. So as you can see, V in is at this point and V out is at this point. So this means that now that I want to keep in my capacitors, so if C in is here, let us call the generator we have to attach, the signal we are attaching to the amplifier, let's call it now differently. Let's call it V in prime. And at the same time, V output, which is the output is measured on the load, let's call this V out prime. Okay. And so let us, to understand the effect of C in, let us look at the input port. Okay. So this input port, this entire circuit, is equivalent to this. We have our generator, the capacitor, and so from this point, what we see is the input impedance of the circuit, isn't it? Which is, as we demonstrated, RB in parallel to HIE. So I've written here just Z input, but we know that Z input is this thing. So Z in would, as we discussed now, would the V in that we used to call today in the simplified circuit without C in was taken at this point. And so effectively the relation between this V in prime and V in is represented here, is the voltage divider between Z in and the impedance of C in. And so that's what I'm doing here, as you can see, is Z in over Z in plus Z C in. And by writing things more explicitly, remember that Z in is effectively this parallel of two resistors. And effectively we get this kind of formula, which we can write better as J omega over omega in divided by 1 plus J omega over omega in. This effectively is what we've seen as a high-pass filter. When we were doing passive filters, this is exactly the type of relation that we would see for a simple high-pass filter. So this means that what we've called V in prime would be identical to what we used to call today V in, only if omega is much bigger than omega in, which is C in time Z input. So you can see how the input impedance of a circuit actually is important, because here defines this omega input. For frequencies, effectively what this is telling you is that frequencies that are much smaller than omega input are effectively rejected by the circuit because of the input capacitor. So the input capacitor disappears effectively, doesn't play any role if omega of the generator is much bigger than omega input given by this. Okay, this is a first important result. So there is a high pass filter due to C in. The other thing is relates now to C out. So let us analyze the output port. So I've redrawn here the output port once we connect C out and RL to the circuit. So there is a bit of analysis here to do. Again, nothing major. The KCL, Kirchhoff current law, VO prime is RL I out, I tilde, sorry, here. And this is what we've seen today, from the relation between IC and IB, based on the simplified hybrid model. And this is just really Ohm's law, and then substituting inside. So this is, Ohm's law. So VRC is either measured this way, Ohm's law, or measured this way, as you can see, and that's what I've done here. So anyway, with some algebra, what we can realize here, what I would like to do is find a relation between VO prime, so the output of this circuit that now contains the output capacitor, a relation between VO prime and V in. So in this situation, we can see that from the analysis I've done there, we can write everything in this form. This is AV infinite, which we've seen today is for the CE1. This is the CE1 fixed bias configuration. The AV infinite was, if you remember, RC minus RC time HFE or HIE. So that's what I've done here. This is AV infinite time this quantity. And if you sort out this quantity, you get you can write it in these terms, and which we see is again a high pass filter. And we can see that VO prime over V in is equal to AV. Remember, AV was VO over V in. Okay. So basically AV is the quantity, the amplification that we would have expected when C out was negligible. And we are comparing it with the amplification when C out is now being taken into account. So these two quantities are identical if omega is much bigger than omega out, where omega out is defined by effectively the inverse of this quantity, as I've written here. So we have another high pass filter now in output. So we have effectively two high pass filters here. One is in the input and one is in the output toward the load. And so in the previous step, by looking at the input circuit, we calculated the ratio between V in and V in prime. now we calculated the ratio between VO prime and Vin. We can now try to combine them to find the ratio between VO prime and Vin prime, which is the total amplification of the entire circuit that takes into account the presence of the two capacitors, C in and C out. And that's what we do here. So we could write AV prime, which is defined as VO prime over Vin prime. Remember that what we are, if we go back to the initial circuit, so we are now trying to calculate the ratio between this VO prime and Vin prime here. That, this takes into account the effect of the capacitors that are there. And so we can do it using the other bits we've done just now. So VO prime over Vin prime can be written as we can multiply and divide by Vin. So I have VO prime over Vin, which we've just calculated here. And then we have Vin over Vin prime, which again we have calculated previously when we were looking at the input port. So in the end, by putting everything together, substituting, we get the total result of how now the presence of these two capacitors, C in and C out, affects the total, for example, voltage amplification of this circuit. And as we already anticipated, both these terms work as a high-pass filter. So there are two characteristic frequencies, omega out and omega in, and we need to make sure that the results we've seen today, when we were effectively neglecting the presence of C in and C out, to make sure that this holds, we need to make sure that omega is above these two, is bigger than the maximum of these two frequencies. And so we should expect that above these two frequencies, the voltage amplification is what we've seen today for the, for example, for the circuit, which is IAV infinite time RL over RC plus RL. But below those frequencies, we should expect that when omega in kicks in, there is a 20 dB per decade effect due to the first filter kicking in. If also the other filter kicks in, then there is an additional 20 dB per decade, and so this will go as 40 dB per decade now. And so we can clearly see here a high pass filter behavior. And so this shows you the importance of choosing C in and C out properly to make sure that the response of the amplifier will be the one that you expect, for example, this one, for the frequencies that you want. Okay, as you can see, above omega out and omega in, the response of the filter is effectively constant. What we did, the results we got today are valid for a large, for a wide range of frequencies. Okay. Because as you can see, the effect of the C in capacitor and the C out capacitor are only able to cut the low frequency part. Okay, we still don't see anything that is going to cut at high frequency. In reality, there is, and that's what I'm going to briefly mention in a moment. And that will effectively define the full bandwidth of the circuit, of the amplifier. But what I want to stress is that the parameters we've put in, which is C in and C out, these are things we decide, have an effect only on how low the amplifier can operate. So it's up to us, depending on which is the lowest frequency we want to go, it's up to us to define omega in and omega out, so C in and C out properly, in such a way that we can push this boundary as low as we can, if we need to. Okay, so this is the key thing to understand. And remember, the omega in and omega out are defined from these equations. Okay. So what is limiting then at high frequency? So this picture is completely true and valid in the framework we are working with, that is the low frequency regime operation of the AC small signal model. We are assuming that we are at low frequencies. We said up to, say, a megahertz, let's say. Now the thing is that the thing we need to consider is that when we go to high frequencies, then there are other things that become important. Which are these things? And this is where we are now dealing with the AC model at high frequency of the BJT amplifier. Again, this is just for your curiosity, so you have a bigger picture, a better idea of what is going on. But the whole point is that we have PN junctions in the BJT. Two PN junctions. We know that PN junctions comprise the entire picture of the PN junction comprise depletion capacitance and diffusion capacitance. So the diffusion capacitance is extremely important in forward bias. In reverse bias, it's only the depletion capacitance. So here is the point is that the effect of these capacitance will start to play a role at high frequency. High frequency means above, let's say, 10 megahertz, 100 megahertz, gigahertz, and so on and so forth. So above, let's say, tens of megahertz, we start entering the high frequency regime, and is there where the effect of these capacitances may play a role, will play a role. There is these capacitances will have an effect on, will start effectively introducing a filter effect, reducing, let's say, behave like a low-pass filter, if you like, as we will see in a moment. The main point to realize is that when we have our NPN BJT transistor operating as a small signal AC amplifier, effectively this is biased in such a way that it is the quiescent point lies in the active region. And the active region, we've said, that means that the B junction is forward biased, which means that there will be a CBE, base emitter capacitance that will be playing a role, that will be the sum of the diffusion and the depletion capacitance, because it's forward biased, that junction. And then we have the BC junction that is reverse biased, and so there will be a base collector capacitance, which will be mainly depletion capacitance, that will play a role. So we need to introduce, if we want to look at the AC small signal model of a BJT transistor at high frequency, we need to take into account these two capacitances. A capacitance between the base and the emitter, and a capacitance between the base and the collector. And so this is the simplest high frequency model for the BJT transistor. In AC, the AC small signal model at high frequency for the BJT in common emitter configuration. As you can see, there is now a capacitance between the base and the emitter, and a capacitance between the base and the collector. Analyzing this type of circuit, for true amplifier application becomes extremely complex, especially because of the presence of this. And this is obviously beyond the scope also of this course. We have seen, though, just to give you a hint, how would you tackle this? We have seen the way to solve this issue here of having this capacitor bridging, if you like, the small signal model, is to use the Miller's theorem. The Miller's theorem shows how to split these things that are bridging a two-port model. So if you are interested, go back to what we did in chapter 1. But what is worth noticing here is that in the end, the effect of the presence of these capacitances is to add a low-pass self-filter effectively behavior because of these capacitances. So there will exist, a omega high frequency, omega HF, above which the system will start to behave as a low-pass filter. And so attenuation will kick in. And so on top of that, there's one more thing that will be happening at high frequency, which we didn't mention until now, is that at high frequencies, HFE will start to decrease. So HFE drops at high frequency. And so putting all these things together, we could, and trying to complete, let's say, the plot, the Bode diagram we were doing previously. So we said that there is a high pass behavior due to the C in and C out capacitors, but now there is also a low pass behavior due to omega HF, which lies in the very high frequencies, maybe gigahertz or so on, but somewhere there. And there is also a decreasing a drop in HFE, which will make drop, for example, the total amplification, the voltage amplification, and so on. So we should always expect that the thing we've seen today that seemed very nice and very simple actually hold true for a certain bandwidth. The low end, the low frequency end is determined by us through C in and C out, the capacitors we put in. The high end is maybe more related to the intrinsic capacitances of the PN junctions that are in the BJT transistor. Okay, so this completes everything I wanted to really, tell you about, and I think completes the picture around the BJT as an amplifier. So I think we've seen some very cool stuff with the BJT in a very simple way as well. So I think that's the thing that is intriguing, let's say, about the BJT transistor, is that it's so simple in a way, but also you can do so many cool things, as we will see next time. So next time we will have a look at some very, very nice applications of the BJT as an amplifier. So that's everything for today. Thank you for watching, and I'll see you next time. Bye.